the ellipse. There are some ellipse notes that you can find in the Documents folder to accompany this if you don't already have them. Okay, for some reason my slide is not advancing. There we go. The first thing I want you to notice is just some applications of the ellipse. I'm going to move this out of the way. One of the applications is that planets travel in an elliptical path with the sun at the focus. Many other planetary bodies travel in orbits that are ellipses or hyperbolas or parabolas as well. Next, architecture. The Romans used arches. So, for example, there's a half ellipse right there, or another ellipse there on the bridge. They used arches in their elliptical arches in their architecture. The Greeks were the ones that actually studied the conics and their mathematical properties extensively, but they didn't really do a whole lot with them as far as practical use, but the Romans put them to practical use in architecture. Another place where we have elliptical orbits is in an atom. Now let's take a look at the parts of an ellipse. So you want to add these to your drawing on your notes. First of all, there is the center, which is in the center, and these 2 points are each called a focus. Plural is foci, F-O-C-I. Not sure if I can write that on here. Yeah, that would be the plural, foci. We also have 4 vertices. The plural is vertices for vertex, 4 of those. We have the axis that goes all the way across from vertex to vertex in the longer direction. It's called the major axis, and I'll bet you can guess what the other axis is called. Bing, 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 bing. Minor axis. Very good. Those are the parts of the ellipse. Now, what I want you to do is choose a point somewhere on your ellipse. I'm going to pick one here. You pick one wherever you want. It could be anywhere on the surface of the ellipse. And I want you to measure with a centimeter ruler from the focus here to the point, and from the point to the other focus. Only draw a straighter line than I did, because you're going to have a ruler. Then I want you to label one of these D1 and the other D2, and I want you to measure them, and I want you to add them up. So I want you to do D1 plus D2. Then I want you to measure the distance of the length of the major axis from vertex to vertex. And you should notice something very interesting. I think I better erase that and move it over. You should notice something very interesting. This is actually a lot more fun when we do it with the whole class, but by yourself, hopefully it can be still fun too. So hopefully this is what you notice. The ellipse, first of all, well, let me go ahead and put on these. The ellipse is the length of the major axis, or I'm sorry, D1 plus D2 is the length of the major axis. Now I want to show you, imagine that D1 plus D2 is a piece of string, and that the ends of the string are tied to the focus. Now if you removed that piece of string from the 2 foci and stretched it out, it would match the length of the major axis. Also, if you took a pencil right here and drew, maybe here's your point of your pencil, and drew around, pulled the string tight and drew around, it would actually trace out the path of the ellipse. I'm going to show you that. I'm going to have to get out of the PowerPoint for just a second and show you an example of that. No. So if we look at this here, you will notice that the points, there's the string D1, D2 attached to the 2 foci, and I've got this pencil and I'm tracing it around, and it's drawing the ellipse. Pretty cool, huh? Okay, I'll put that back down, go back to our PowerPoint. Now on the PowerPoint, the next thing we're going to look at, finish that, the Whispering Gallery. Oh, got to escape for a second again. There's an interesting story that goes along with the Whispering Gallery. No. Let me get this one. Oh, it's still moving. I better stop this. That's interesting. I don't want that on there. I haven't tried doing this with a smartboard before, so the moving things around is kind of an interesting process here. I want to find another one of these, but I'm not finding what I want. So back to the drawing board. Interesting properties of conics. There's what I'm looking for. Okay. If I were to stand at this focus and whisper, and I'm in a room that has an elliptical ceiling, a ceiling that has a curve shaped like an ellipse, and I'm standing up, you almost have to think sort of three-dimensionally here. I could whisper, and someone at this other focus could hear everything I'm saying, and this is why. I'm going to push this little button here, and you're going to see little red dots come out from focus 1. So we're going to pretend those are sound waves. So all these different sound waves come out from focus 1, and look where they all end up. Right at focus number 2. It turns out that anything that bounces off of one focus and over to the edge of the ellipse will bounce to the other focus. And that's a reflecting property of the ellipse. So there was actually a whisper chamber in the Statuary Hall in the Hall of Congress in the United States and in Washington, D.C. And sometimes presidents would put their desk at one focus and their waiting room for visitors at the other focus, and they understood that they could eavesdrop and hear what their visitors were saying clear at the other end of this very large hall. Kind of interesting. So that's the reflecting property of an ellipse. Okay, we're going to go back to our PowerPoint now. Okay, in our PowerPoint, let's go to the next slide. If you go to your notes, you'll see at the bottom left-hand corner, you'll see this little ellipse, and I want you to label. Notice that we have an equation, x squared over a squared plus y squared over b squared equals 1. So what do the numbers a and b tell us about the graph? Well, a tells us the distance from the center to the vertex on the major axis, and b tells us from the center to the vertex on the minor axis. And c, which isn't in the equation, tells us the distance from the center to the focus. And we're going to figure out in a little bit how do you find c. Looking at the other equation, or the other graph that you have in the lower right-hand corner of your notes, notice the difference here. Now the major axis is in the y direction, so we put a under y, and then we put b under x, although it really doesn't matter just as long as you remember that a is the larger number in the ellipse. So if we go ahead and add a goes in the half the length of the major axis, b is half the length of the minor axis, and c is the distance to the focus. So add a, b, and c to your graph. Something to notice is that in the standard equation of ellipse, a squared is always bigger than b squared. Now let's do a little practice. I have to keep moving this crazy thing around because it's always in different places. Little arrows are going to come out, and you're going to name the parts of the ellipse. So practice. Yep, center. Vertices. Foci. Now what letter represents the indicated lengths here? So that length would be A, B, C, A again, B again. Not C, fooled you. 2A, because if this direction is A and that direction is A, then the length of the major axis is 2A. Kind of an important little piece of information to hang on to in just a minute. Now go to the back side of your note where it says finding foci, and we're going to look at a couple pieces of information here. First of all, we know that the distance from the center to the focus is c, and the center to the vertex on the major axis is a, and the center to the vertex on the minor axis is b. But how are these three related? Well, I want you to recall that the length of the major axis is 2a, and 2a is also, and the length of the major axis is also the distance d1 plus d2. If we picked a point somewhere on the ellipse and we stretched a string from the focus to that point and then over to the other focus, that is d1 plus d2. And since d1 plus d2 equals the length of the major axis, or 2a, what if we position the string so that it went up to the very point where B is and back down again? So notice we've taken the string basically and divided it in half. So if the string has a length of 2a, and we do that, then this piece of string, this distance should be a, and this distance should also be a, because the total length of the string is 2a. And that allows us to create a Pythagorean relationship. B squared plus c squared is equal to a squared. And we can then figure out what c is based on knowing a and b. So subtracting b squared from both sides and taking the square root, we get c is the square root of a squared minus b squared, remembering that a is our bigger number. Now let's do an example problem putting all of this together. So we have x squared over 9 plus y squared over 36 equals 1. Well, these are, the 9 and the 36 are the a's and the b's. We say that a is the bigger number, so a is equal to plus or minus the square root of 36, which is plus or minus 6. B is equal to plus or minus the square root of 9, or plus or minus 3. Since the 3 is under the x, that means we go 3 in the x direction, and since the 6 is under the 9 or the y, we go 6 in the y direction. 5, 6. 1, 2, 3, 4, 5, 6. And we draw our ellipse, being careful not to make it too pointy at the top. It actually is a nice round curve at the end. There we go. Oh, that's lovely. One of my better ellipses, I think, if I do say so myself. Then to find the foci, we say c is the square root of a squared minus b squared, which would be the square root of 36 minus 9, which is the square root of 27. And we know the square root of 27 is a little bit more than 5. It's, I think, about 5.2. That's good enough for my purposes because I'm just going to graph then my two foci. Notice they go on the major axis. And one other interesting point about foci, if the ellipse is long and skinny, the foci are close to the vertex. But if we were to slide the focus towards the center, our ellipse would get rounder and rounder, and it would end up, oh, look at that little circle I have there. It would end up actually, if we move the foci all the way to the center, it would end up being exactly a circle. One more example problem. A large hall has an elliptical ceiling that is 100 feet long and 60 feet wide. A pair of inspired pre-calculus students decide to see if two people standing at the foci of the ellipse can really hear each other whisper. They correctly calculate the focal length, and the two students stand at the two foci. Brilliant students, don't you think? How far apart are they standing? So we're going to start, whenever you have a story problem, sketch a picture. It's very important. So I'm going to make a picture of my ellipse. Now realize that we're thinking three-dimensionally. This is really an elliptical ceiling. The students are standing on the floor and they're sort of inside an elliptical three-dimensional ellipse. But we can represent it fine with a flat ellipse as far as solving the problem, because they're standing on the floor, which would be underneath the arch of the ellipse. Anyway, in our ellipse, we have, I drew an axis on here because it's very convenient to center an ellipse at the origin when we're doing a story problem. It says it's 100 feet long, so my longest part of the ellipse is 100 feet, which means it's going to go 50 in each direction from the center. So this would be the point 50, 0, and this would be the point negative 50, 0. And it says it's 60 feet wide, so in the shorter direction, the minor axis, we're going to be going 30 feet in the y direction, both directions from 0. So that means a is not 100, a is not the square root of 100, a is half of 100, it's 50, and b is half of 60, which is 30. So if I know what a and b are, then I can say c is the square root of a squared minus b squared, which is the square root of 50 squared minus 30 squared. Do the computations and you'll find out that's 40. So the distance to the focus is 40 in both directions, which means the students are standing 80 feet apart. Brilliant pre-calculus students. And that is the end of a quick and fast introduction to the ellipse and some of its beauties.